Let's talk about one of the biggest, thorniest problems in AI right now, hidden bias. Today, we're digging into a really cool new technique called dynamic focal loss. It's all about teaching AI how to learn more fairly, especially when the data it's learning from is seriously lopsided.
So, here's how we're going to break it all down. First, we'll get right into the heart of the AI bias problem and look at some of the early ways people tried to fix it. Then, we'll explore how an AI actually learns, which is going to set the stage for this new solution. After we see the pretty impressive results, we'll talk about what this all means for building a future with fairer AI. All right, first up, let's really unpack this fundamental issue, the one that can make AI systems not just a little bit inaccurate, but genuinely unfair. I mean, really think about that for a second. The stakes here are incredibly high. We're putting AI into everything, from our hospitals to our banks, so if the core models are biased, the fallout can be massive. And look, this isn't some far-off sci-fi problem. These are very real-world examples that the research points to. A biased medical AI could literally miss a rare but deadly cancer just because it hasn't seen enough pictures of it. It might let a clever new type of financial scam slip by. Or even worse, it could actually amplify the societal biases already present in the data, creating this awful feedback loop of inequality.
So, where does this bias even come from? Well, more often than not, it all comes down to the data. See, an AI learns from the examples we feed it. And if that data is imbalanced, meaning some groups are just massively overrepresented, the AI ends up with a really skewed, warped view of the world.
Let's make this super clear. You have the majority class. That's all the common stuff. For a medical AI, that's thousands upon thousands of scans from perfectly healthy patients. The model learns this stuff, no problem. But then you have the minority class. This is the rare stuff, but it's often the most critical. Like that one scan in 1,000 that shows a very unusual tumor. It just gets drowned out by all the noise. So what happens? The model becomes an expert at spotting what's normal, but it's terrible at spotting what's rare, which is usually the very thing we built it to find. Okay, so people have known about this problem for a while, right? So naturally, they've been trying to solve it for a long time. Let's take a look at some of those first attempts to try and even things out. The first ideas were pretty intuitive. You just try to fix the data itself. One way is oversampling, which is basically just making a bunch of photocopies of the rare examples. Or you could do the opposite, undersampling, where you just start deleting the common examples to try and balance the numbers. Some even tried generating brand new, totally artificial rare examples to pad the dataset. But these simple fixes came with their own huge headaches. If you just copy the rare data over and over, the model can overfit. That's like memorizing the answers for a test instead of actually learning the subject. And if you start deleting the common data, you risk throwing out really valuable information that the model actually needs to understand the full picture. It was a real catch-22. This is where the story gets really, really cool. Since messing with the data is so tricky, researchers started thinking, what if we could change how the AI learns instead? And the absolute key to that is something called the loss function. The best way to think about it is as the AI's teacher. And hey, don't just take my word for it. The authors of this paper put it perfectly. The loss function is the single most important thing that guides how a model improves. It's the rulebook for how to get smarter, mistake by mistake. Now, the standard teacher that most models use is called cross-entropy loss. And its big problem? It's kind of lazy. It gives every single mistake the exact same amount of attention. So if the AI is already an A-plus student at spotting healthy scans, but is feeling miserably at spotting rare diseases, this teacher doesn't care. It just lets the model keep acing the easy stuff and ignoring its biggest weakness. Then came a major upgrade, focal loss. This is a much smarter teacher. This teacher basically tells the AI, hey, you've already mastered the easy stuff. Let's stop wasting our time there and focus all our energy on these really tough examples you keep messing up. And that was a huge leap forward. But even that focused teacher wasn't perfect. And that brings us to the real star of the show today, dynamic focal loss, or DFL. This isn't just a smarter teacher. It's a master teacher. DFL does two brilliant things at the same time. Just like focal loss, it zeroes in on the hard individual questions the AI gets wrong. But, and this is the game changer, it also zooms out, looks at the bigger picture and says, you know what? You're consistently weak in this entire subject, the minority class. We need to put in extra credit work right there. It's this powerful dual action approach that makes all the difference. And you can actually see this in action right here. This chart is super revealing. It basically shows how much attention each teacher gives to a mistake.
Now, look at that green line. That's our dynamic focal loss. See how it stays higher for much longer as an example gets tougher? That means it's forcing the model to struggle with and really learn from the hard cases, especially the rare ones, way longer than any of the other methods.
So, just to sum up its superpower, DFL has this incredible two-pronged attack. It's constantly adjusting its focus based on how hard each individual example is. But at the very same time, it's looking at the whole class picture and giving a special boost to the subjects that are being neglected. It's tackling both the hard questions and the weak subjects all at once.
All right, so the theory sounds amazing, but the real question is, does it actually work? Let's get to the proof. This is where we see how dynamic focal loss stacked up head-to-head against the older methods in some seriously tough experiments. The researchers didn't go easy on it. They took a standard AI model and they tested it on a dataset that was intentionally made super imbalanced. We're talking in some cases 100 times more examples of the common stuff than the rare stuff. And to measure success, they used something called the F1 score, which is just a really smart way to grade the AI that penalizes it if it only gets the easy common stuff right.
And boom, the results are just crystal clear. On the hardest dataset, the one with that crazy 100-to-1 imbalance, dynamic focal loss, RDFL, just blows the others out of the water. It scored almost 69, which is a significant jump over its predecessors. It's a really decisive win. But honestly, this next part might be the most incredible finding of all. You'd think this smarter teacher would be way more work, right? Nope. This huge improvement in fairness and accuracy costs almost nothing. The study found that using DFL only added about 2 to 4% to the total training time. That is an absolutely fantastic trade-off.
So let's zoom out. We've gone through the tech, we've seen the results, but why does a breakthrough like this actually matter in the real world? It matters because it gives us a powerful new tool to solve the exact problems we talked about at the very beginning. With a method like DFL, we can start building much more reliable systems for spotting rare diseases, for catching complex financial fraud, for finding tiny but critical defects in a factory, or even for forecasting rare but catastrophic events. Look, dynamic focal loss is a massive step forward. It's a smarter way to teach our machines, especially when it comes to the rare stuff that so often matters most. But like any big breakthrough, it also gets you thinking about what's next. We found a better teacher for our AI. So what's the next great challenge we have to solve on this road to building a truly unbiased AI? And that's the question we'll leave you with.